Hello, everyone, and welcome back. We heard you guys were hard at work in the breakout room and can't wait to see what you've come up with. But first, let's throw it back to Pat and Owen and Sophia, who are two of our college mentors. And I also want to thank Sanahi for helping to lead that breakout room.
Hello, hello. And let me share. Where is my menu there for share? Got it. And there we go. All right, can anybody see the robotics slide?
Yep.
Let me make sure. Got it. Thank you. Well, welcome back, everybody. And so I know you had a little bit of time to hopefully gain some knowledge with not only the platform, but how to use those blocks and get some things done. But before we look at your wonderful work, I would like to allow our college mentors to introduce themselves and if you have questions about where they're at, what they're doing, what they're involved in, there's a lot of cool stuff that they're doing. So maybe we can start with Sophia, and you can jump in and tell us a little bit about what you're doing, what you're up to.
Awesome. Thanks, Pat. Hello, everybody. My name is Sophia. I'm currently a senior at the University of Notre Dame, and I'm studying aerospace engineering. Next slide, please.
Excellent. Yep, got it. Hold on. There we go.
Thanks. All right, so just a little bit about my engineering timeline. So I graduated high school in 2021, so kind of a long time ago. I'm from Findlay, Ohio, super small town in Ohio, Northwest Ohio. So I went to Findlay High School. And in high school, I had no idea that I wanted to do engineering. I was pre-med all the way up until my senior year of high school. So I did a lot of volunteering activities. I volunteered at the hospital. I was in like the biology club, the anatomy club, literally nothing to do with engineering whatsoever. But then when I got accepted into Notre Dame in 2021, I decided to switch to aerospace engineering. I've always really liked space. And I kind of decided that I like space more than I liked medicine. So I picked aerospace engineering. And one of the first things I did at Notre Dame was I joined the rocketry team here. Every year we design, build, and launch a rocket in one of NASA's student competitions. So I've been involved with that all 4 years here at Notre Dame. And that's definitely my biggest engineering club. I have a lot of fun with it. So then in 2022, my sophomore year of college, I was doing rocketry. And then I would say the highlight of my year was during the summer. I had an internship at a company called Maxar. It's a satellite manufacturing company out in California. So I was working with their electrical development team. We were writing test scripts to test all of the satellites before they launched to space. And that was really cool. And it definitely confirmed my passion for aerospace. After that, I was like, okay, I know I'm in the right field, and this is definitely what I want to do with my career. And then my junior year, last year of college, I was a design lead for the rocketry team. So I was in charge of a group of like 20 to 30 students, and we built a payload for our rocket. So I spent a lot of time doing that. It was very fun. And then over the summer, so this past summer, I did a little bit of research. This was my first time doing research. And I was in a lab at Notre Dame, looking at jet engines and turbo machinery and things like that. And if you guys don't know what that is, I can explain it all later, and feel free to ask any questions. So then currently I'm in my senior year of college, still doing rocketry, and right now I'm focusing on applying to grad school. So for me at least, I think that I don't want a job right away after college. So I'm going to delay getting a job by just doing more school. So I just applied to a bunch of PhD programs, and I'm waiting to hear back from those. So that's where I'm at right now in my engineering journey. Next
Yeah.
slide, please.
So Sophia, I have a quick question on you, and I don't know if others,
Yeah,
but how you said there's a competition that you do your rocketry. Like, what do they measure? How do you compete? Like, what are they measuring?
that's a good question. Yeah, so we compete in NASA's Student Launch Initiative. I think there's about 50 schools in it, and they give us a challenge at the beginning of the year, a payload challenge. And it's normally like some sort of science experiment. So we get scored on. So we spend the whole year designing, building the rocket and the payload, and then we launch in Alabama at the end with all the other schools. And they score us on how well our payload does, so how well we accomplish the science experiment, how high our rocket goes. So it's really cool. At the beginning of the year, they ask us to set a target altitude for our rocket. So we'll say, we think our rocket is going to go 5,000 feet. And then we get scored on how close we are to the 5,000 feet. So we have a really cool air braking system on the rocket. It's like a massive controller that computes how high we are and how much drag it needs to produce in order to hit our height. So that's a really cool part of the rocket. And then
Yeah.
we also have a bunch of reports throughout the year. So we do a lot of writing, a lot of technical presentations, and we get scored on all of that. But overall, it's really fun. And if you're into rockets or aerospace at all, I definitely recommend joining a rocketry team in college. Most colleges have them. And for me, it's been a great way to meet friends and then apply all of my aerospace principles to a real thing.
Awesome. That sounds really cool. All right, let's go to the
Yeah,
next.
one more slide.
Yep, there you go.
Cool. Yeah. And then here are just some photos of me doing engineering things. So the one in the middle with the big satellite, that was from my internship at Maxar during my sophomore year. And that was one of the satellites we got to work on. It's really cool. It's actually the largest communication satellite. So we got to work on that. And while we were there, we actually got to see it launch to space. So that was a really cool moment. And everything else was just me doing a bunch of rocketry stuff. So feel free to ask any questions today, guys, about rocketry, engineering, aerospace, you name it.
That sounds great. All right. Well, I think we're going to jump to, thank you for all of that, Sophia. Appreciate it. I have lots of questions, but we don't have we don't have time for all my questions. But let's go to Owen. Owen, tell us a little bit about yourself.
Yeah, thank you, Pat. All right, so my name is Owen. I'm a freshman at Stony Brook University, and I'm a mechanical engineering major.
Okay.
Next slide.
Into aerospace, 3D printing, and robotics. So tell us more.
So right here, I have a lot of my high school experience, given that I'm a freshman. I haven't been in college for too long, but I did just come out of high school. So you could see that a lot of the things I was into, it was a lot of STEM stuff. So unlike Sophia, I knew I wanted to do something engineering, math, something like that. So I was in the robotics team, I did chemistry club, I was in the math team, and I was taking a lot of AP classes that were in those STEM fields like calculus, chemistry, computer science, all that good stuff. And then I also have my school had like a media team, stuff like our YouTubes and socials. So I found myself with a leadership role in there, and I was developing new things for the school and a bunch of stuff for that. So I also have that leadership opportunities there. So in high school, I really tried to put myself out there and do as much as I could to set myself up for success later on in college, which paid off. If you could go to the next slide.
Yeah, of course. So, um, oh, one more. There you go.
Yeah. So this is all the stuff I've been doing here at Stony Brook. So you can see I've been doing a lot of Arduino and like my mechanical engineering classes. I have a robot there, that second picture that was made to like sweep off the floor. It's like these small projects. And then I also in the middle there, that was for my school's robotics team. We made a robot. We just controlled how it moved with the wheels. We had a software to control it, and then we competed against other robots. It was a lot of fun. And then I also have I did the NASA space program, which was learning how to write um like proposals, how to propose a new technology. So I got in a group and we all thought of something that NASA was missing and how we could fix it. We developed that solution, we developed a proposal for it, and then we proposed it to a board. So that was a lot of fun, a lot of learning, and all that engineering I've been doing in high school really paid off for me and really set me up for success. And if you have any questions about any of it, high school, what you could do in high school, what options there are in college, I'm here.
Great. That's a lot of fun stuff you're doing. I want to go back to high school and do more of that stuff.
Yeah.
I'll just have to do it in my own high school. But quick question for you. What languages do you feel like you had to learn when you were doing all these types of things and even now your freshman year at Stony Brook?
What do you mean languages? Like programming?
Coding
Yeah,
languages. I guess pertaining to what we're talking about today, I thought that'd be
right.
interesting to see
Yeah.
what you've gotten involved in.
Yeah, so I had a lot of so like for example, I started with computer science, CSA. So I
Hmm.
learned how to do Java for a class. And then during that year, I also did an extra program. Some people came to our school and taught us how to do JavaScript, a branch of JavaScript. And then next year I learned Python and some coding based languages like you did today. I've done CSS and HTML. It's a lot of programming languages, and once you learn one of them, you kind of learn them all. Not really, but you really get the hang of it. It's really the basics, and then you can apply it everywhere.
Sure. It's the logic is pretty similar throughout. It's just
Yeah.
a language thing. So very good. Thank you for that. And hopefully, again, anybody out there, students, if you have questions on what these guys are involved in, I'm sure there's a lot more to their story. But let's get to what you guys produced. And so And by you guys, I mean, the stuff that hopefully you were able to get involved in the time we had together, or you had together was, we talked about robots, and our hope is that you were able to use a bit of code to make some shapes. And if you had an opportunity to do the maze, I think that'd be great. There were different backgrounds that allowed you to kind of engage with it in different ways. And so let's ask you this question right now. If you don't mind helping me out, go to the Slido and let us know what kind of shape did you start with. I feel like that would have been a good way to begin learning like what to do.
You're muted.
Thank you. Oh my gosh, I was muted the whole time.
Just
Well,
for like the last 30 seconds or so.
yeah, no, I got you. So yeah, my hope is that if you take a look at the Slido, one of the first things you may have done is make a shape, and I'm curious to see where you started with. And there are different ways to do it. And I would love to see what you guys came up with, because there's creative ways to make the same shape depending on how you went about it. So most people made a shape unknown to mathematics. I did that a couple of times when I was playing with the code, that's for sure. Try to make a very large-sided object, and you're like, what? That doesn't look like that at all. So we got some rectangles, we got some polygons and things like that. Five-sided plus. I guess we would just jump past the triangle, but one of the things you had to consider was, okay, well, what angle do we use? And so that may have been something that you played with and experimented with, because you weren't sure about it maybe. And you're like, well, I think it's 60, 120, but is it possible to see some of your code? Can any of you share with us what you have out there?
Yeah,
Teachers and students, is it possible to be able to do that?
yeah, not to put you on the spot, but if Archbishop Stefanak, I see you here, we had a few classes that said they're taking lunch right now, they're gonna come right back, but I see you're here, and I think you were active in that breakout room we heard, so not to put you on the spot, but if you have any brave volunteers to come up and talk us through the process, we would love it.
And I would love to see these shapes that are unknown to mathematics, because like I said, I produced a few of them. So I think I may have reinvented math, or my code went awry. So we'll see. But feel free to tell us the successes and the things that maybe didn't go the way you thought, because that's how we learn.
Absolutely. And while we wait for any volunteers, I do have some questions that students submitted previously that I can throw to you all, if that's okay.
Yeah, please.
Um, yeah, let's do this. So, is writing a program or coding for a robot the same as using AI? And that was from Challenge Prep Academy in Georgia.
Well, Owen, Sophia, what do you think?
Are you going for it, Owen?
No, I was gonna ask for the question again.
Oh, sure. So, this is from Challenge Prep Academy in Georgia. Is coding or writing a program for a robot the same thing as using AI?
My opinion, I don't know too much about AI. I've never used it besides just like typing into Chat GPT. But I would say they are different. Um, Different but similar in some ways. When you're coding a robot, you're intentionally writing a code to make something do something. And AI is kind of doing that all in the background for you. So you're not actually coding AI. But in a sense, AI in the background does a similar thing that a robot does. So there's a script somewhere making it compute whatever you type in. They just have different applications. Yeah. Do you want to add to that, Owen?
Yeah, just kind of like using an AI is like using a finished product, whereas when you're coding, you're kind of like you would use coding to make the AI that somebody could then use. So it's kind of like two different parts of, it's two different steps.
Kind of just two applications of coding. So with the robot, your robot is your finished product. But then behind the scenes of AI, there's people writing software to create the AI. So they're just two different things that have coding in the background.
Yeah, and I guess I'll add to that just a little bit of my experience. Sometimes you can prompt an AI, chat GPT for something that you'd like to do, and it's not correct. It comes out a little bit wrong, and you as a human, knowing what the end product should be, needs to be, pull that together and coalesce in a way that makes sense in the end. So it can be a part of the process, but by no means is it the final one, I think.
Those are really, really good responses. I have another one for you. This is from Uplift Mighty Preparatory High School in Texas. They want to know, how can techniques used in robotic coding be used in the medical field? That's a good question.
I'd love to go back to Sophia. When you're on the cusp of getting into these professions, what do you guys think? What have you seen and heard?
That's a really good question. So a lot of surgeries nowadays are becoming robotic, which kind of takes away from the doctor, but it makes sure that everything is really precise. So a lot of the microscopic surgeries are using robots, to do the surgery, which is a little bit scary. But it
A
helps the
little bit.
doctors a little bit and just make sure everything is very precise and done the same way every time. But yeah, the research is really cool. So if you guys ever get the chance, I would look up different types of robotic surgeries because the technology is becoming more and more advanced all of the time. And it's pretty crazy how we can take these complex surgical procedures and make them roboticized. So,
Yeah, just
Yeah,
to add on to that, you see a lot with robots. You can give it an instruction and it'll do the same thing every time, assuming everything's working right. So that's something like Sophia said, they're starting to do surgeries with these robots because they know that if they tell it what to do, it can do that every time and there's less room for error. So these fields are really coming together and they're merging in that way.
There's also a really cool club at my school. Oh, and I don't know if you guys have something similar. It's called Engineering Without Borders, and they make prosthetics, robotic prosthetics for people that have disabilities or they lost a limb or things like that. So that's just another way robotics can be used to help people in the medical sense.
and maybe Sophia and Owen and anybody can help answer. Like and I'm not in the medical profession, so that's still a world that I'm investigating. If you have a robot and you're having it do a surgery, whether it's, making an incision and doing something even minor, every body in I mean, human body is a little different. You'd have to really have a code that is adaptable to that particular human, right? And what they're doing. And I'm curious to see how that would turn out. Like, what would you have to do to know the environment you're in as a robot and not be off by a centimeter or two, if you know what I mean. I don't know if you guys have any insights into that.
Um, Yeah, I don't know too much about the
Yeah,
current metal technology, but I do know that like a lot of the robots will take like a doctor will be doing it like behind like VR or something, and they're simulated it. So they're doing like the movement, the incision, and the robot is going in on that small scale and doing that same action, just maybe without a little bit of that shakiness that the doctor might have or any imperfections, and the robot just kind of corrects that and does it perfectly right on the patient. So it's still a lot of it still comes down to the doctor, but the
sure.
robot is just kind of the vessel for doing that precision.
Awesome. Okay, I'll throw you one more. And then if you guys want to go back and cover any more slides, we can
Yeah.
definitely do that. But again, if any schools, you pop back in from lunch and you're ready to share with us, please feel free to come on up and unmute and talk to us or through chat, whatever you're comfortable with.
Hmm.
One more question for you guys. Pre-submitted, I think it's Munchkin College Prep in Illinois, forgive me. Is Python or JavaScript more widely used in robotics, and why?
My impression is Python is used, but in fact, our guest speaker who works with Boston Dynamics and has done a variety of things. Hopefully, he'll articulate to us that there's actually a variety of coding depending on the application, whether you're talking about a specific motor or a processor and things like that. So it kind of depends on, in my experience, what you're actually coding. I think there's you could do equal amounts of both, but I think Python is pretty ubiquitous. But Sophia, Owen, what do you guys think?
I'm not too sure what the standards are, but I know like it's really going to depend on what you're trying to do. If you maybe want to control the robot through like a website or something, you may want to use more JavaScript because it's more suited for that. But if your robot maybe has to like take in a lot more inputs and does a lot more math, you may want to do more Python. It really comes down to the what your robot's doing and the person who's making it.
Yeah, exactly. Yeah.
Awesome.
Sophia, okay. And yeah, Julie, do you have any questions? You want me to kind of enter?
Yeah, go
through
ahead,
the-
Pat, and I'll let you know if any schools pop
Yeah.
in, want to share or have questions. But yeah, go ahead.
There are some questions, and it allows us to kind of get a feeling for how you're doing with this stuff. And so, if you don't mind engaging with another Slido, please, it'll ask a few questions about how did it go? How did did you try the maze? Did you try to move your sprite around? Give us a little general feedback, if you would, please, about how the project went, what you did. And I think I got to press play, and it is live. So if you can, please let us know. And hopefully it's on now. There we go. One of the things, I know we had a few projects for you guys to involve yourselves in, but hopefully you saw the the landscape. You could do so many things with this. I feel like coding is like being an artist with an infinite number of paints to mix and match. Just make whatever you'd like. So no, let us know. It was hard to maybe, some of the challenges you have are what we all have. So there's no shame in that. Some of you easily got my sprite to move through the maze. That's pretty cool. Okay, gotcha. Share. So we're getting enjoyed learning, easily got my straight through, had to redo. Yeah, I mean, look, you got to redo your code a few times. That is the life of a computer programmer. Uh, both my brothers have been doing it for over 25 years, and the amount of late nights of just redoing code is a tough battle, but there's a lot of satisfaction when you get it working, especially in my view. If you throw your code onto a robot and see it physically engaging with the world around you, I think is just such a cool thing, even in a small way. Um, so yeah, thank you for jumping in on a few of those questions. Is anybody want to share what they did? It seems like some of you did a great job navigating the maze or making your shapes. Does anybody out there want to show us a little bit of your code? I'm looking, I would love to see some of that creativity out there.
Yeah, and it's your lucky day. Don't be shy. We have a small crowd here
Yeah.
because of the weather, so it's just us and Pat and Sophia and Owen. We won't bite, so feel free to come up
Oh
and
my goodness.
talk with
Yes.
us. And if not, I will ask, I promise, final question.
Mhm.
Especially Sophie and Owen, while we have you, and you're, just a few years older than our audience here in high school, what's some advice you have for them when it comes to thinking of their future, major in college or career pathway they may want to take?
I can start with this one. That's a great question. I would say my biggest piece of advice going into college, is to don't be afraid to try new things. I know it's like pretty cliche, but the more things you try, the more you're gonna know about yourself, and the more you're gonna learn what you like and what you dislike. I've had a lot of friends that have said yes to internships, even though they didn't really want to, and they've ended up really loving them. I've also had friends who have tried a club and they realize that they hate that. So anything you do is going to give you more information about yourself and will help you decide what you want to do later on in life.
Yeah, I'd like to say that it's never really too early to start thinking about college in your future, because you may think you have a lot of time, and then you get into like your senior year, and then all of a sudden you're applying, and acceptances are coming in, and everybody's going in these different places, and it's gonna feel like it came really quick, but you should have really been preparing for it earlier. But you should also not worry about it too much and know that there's time and there's chances to change. You can change your major, you can even change schools, like it'll be okay, but you have to make sure that you're on top of it.
And I guess I'll add to that because I've seen over the last 20 years students come and go and engage with what you guys are doing, wonderful things out there at the university level. And I would say don't underestimate different variants of skills. If you have a summer job working at a machine shop or working with an electrician or doing those things where you're handling tools and doing some projects like that can come in handy down the road when you're trying to build a robot, when you're trying to work on a satellite, all those things, all those little skills you'll learn along the way can be very valuable. So don't underestimate the ability to use a tool. And I don't know if Sophia and Owen would agree, but yeah, depending on the project, sometimes that could be very helpful.
That is great advice. I do see a question in the chat. How do you balance work and play in college? Very important skill to have, that balance. How do you guys do it?
Yeah, that's another really good question. Um, for me, I just make sure that I'm involved in my engineering clubs and academics and things like that. But I also make sure that I'm involved in other things too. So freshman year, I joined the club soccer team at Notre Dame. And that was a really nice way for me to have an outlet from engineering. So my week wasn't just engineering every single day. I like broke it up with soccer. And then the weekends, I always make sure I hang out with my friends, do things in the city around South Bend rather than just being in the library and studying all the time. So just make sure that you balance it out. You can have your engineering clubs, but make sure you're involved in other things too.
Yeah, I'd say for myself, like back in high school, I was a bit of like a procrastinator and I just kind of take things as the day came. But then college really forced me to start looking forward and look at what I have to do in my week. So I'd look at all the homework I have to do. I'd look at when clubs are meeting, everything I'd want to do, and I'd be like, okay, I'm gonna do my homework a week early because I know this is really gonna annoy me in a week. So I'd make sure I had everything done, and then when the fun came around, I was free. I had nothing to worry about. So it was able to all work out for me that way.
Awesome. Very nice. Pat, I'm going to throw this question to you that's in the chat because I know you have a lot of experience with competitions.
Yes.
How important do you consider robotics competitions to be for students?
Oh my gosh. I was just thinking about that because I was thinking about Sophia Noah and what they get involved with rocketry and robotics competitions. And I mean, whether the the ability to realize like the competitions themselves, no matter what it is. I mean, my students, we do Vex Robotics, and that's one thing, or First Robotics is another avenue. We do an autonomous vehicle competition. And even with the Rube Goldberg team, I did. The the idea that the students will come in and think, hey, I can do this, and then almost immediately things don't go well. And the sooner you can adapt to that, the sooner you realize, and this is a sign I have in my classroom, fail sooner, succeed faster. And it's something you've probably heard before. And it sounds negative, but it's something that, the sooner you can realize everybody around you, even the ones that are at the top of the heap in terms of success, have failed many times. And so those competitions can be incredibly valuable into just becoming more resilient. And when you can pivot and work on, all right, well, that failed. Let's try to figure out this way. The quicker you can do that, I believe the more effective of a teammate you will be and more successful you'll be. So that's my view of all competitions. Win or lose, first place, 100th place, it's getting through and working through those issues that are going to make you a better engineer.
Absolutely. Thank you so much for that. I have to thank Sophia and Owen. Thank you so much for being here for the Q&A. That was amazing. You gave some really, really good advice and you answered the questions thoroughly. Thank you so much. Pat, I believe it's time and our keynote is here. So I will throw it to you.
He is there. All right.
Yes.
So, do I stop sharing by the way at this point? Do you want me to
Yeah,
jump
let's
off
do
or
that in case Josh wants to share. Yeah.
he hops in? Yeah. How do I stop sharing? Okay. So, yes, Josh Keating is going to be our speaker today, and there's Josh. He is, and I'll do just a brief little intro from what I know about him. He spent years kind of getting into robotics a little bit. And then when he finally, got into university level, he realized, hey, this is something I really want to sink my teeth into. And he's turned that into a professional life that I am jealous of. He does a lot of fun stuff, including with those robots we saw earlier at Boston Dynamics. And so I'll let him discuss his path, but everything we've been talking about in terms of design, build, coding are things that he's worked on, whether it's a satellite or a robot. And so without further ado, please welcome Josh Geating. Thank you for joining us, Josh.
Hey, everybody. Nice to see you all. Nice to meet you all. Thanks for the intro. Can you guys see my screen presenting here? Is that working?
Yes, we can.
Awesome. Okay, great. Like Pat mentioned, I work for Boston Dynamics on the Atlas team. You guys have been doing a lot of work learning about the software of these robots. I work on the hardware team, so I'm really excited to kind of show you a little more about the other giant half of robotics, which is designing the physical robots, designing the parts, integrating it all together. So that's what I'll talk about today. Before I jump into the presentation, though, I just wanted to show a brief video to give you guys a little bit of an idea of what types of robots we build at Boston Dynamics for those of you who aren't familiar with our work.
Into your eyes, all the things you feel my mind. 새로운 만남들은 나를 충전해. Double bump into something, new possibility. 어떤 날 발견할지 뜨근데. Full energy, higher estimate. Better focus on what's charging me. 가끔 길을 잃을 때면 I got you. 영혼의 쥐돌 따라가. 쉼없이 달려가다. 네가 지칠 때 내가 네 휴식이 돼줄게. I'm on it. Just my chance. I'm on it. Takes me there. 내가 원하는 건 simple. 멀리보다는 함께 가고 싶어. I am Nick, 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 I am Nick. Yeah.
All right. So hopefully that gives you a little bit of idea of what we do here at Boston Dynamics. We design, build, and program highly dynamic robots that have arms and legs, robots that move very quickly, very precisely. A lot of the world is kind of aware of us from the elegance with which our robots move. They look very biological, very fluid, and that's something we take a lot of pride in. Before I jump into talking about BD, though, I want to give you a little bit of an overview, what I'm going to talk about, and then I'll jump a little more into my background. So I'm going to tell you a little bit about my personal journey from childhood through to working here at Boston Dynamics. I'm going to talk a little bit about how robots work, a little more focused on the hardware side of things. I'll tell you a little bit about the day-to-day of a mechanical engineer, what our 9-to-5 looks like. And then I'll tell you a little bit about just lessons learned and some observations from my personal journey in career. So I'm going to rewind way back to my childhood, my background. That's a big part of who I am as an engineer. And then I'll move a little more into Boston Dynamics stuff. Yeah, so I was one of 5 kids, grew up around a lot of noise, a lot of chaos, a lot of fun, a lot of laughter, a lot of crying and tears. And I really appreciate my upbringing, and it's a lot of who I am today as an engineer. My parents are very, very different people that complement each other well. My mom was raised in India. She grew up in pretty severe poverty where, she was, it was kind of a miracle that she got an education at all. I'm not going to go through a whole story, but she really raised us with a lot of discipline, a lot of focus on education. I attribute most of my work ethic to the way my mom raised us. If we got a 98% on a test, she would ask us, what did you get the 2% off? And there were some good things about that, some bad things about it. But I really attribute a lot of the perseverance and rigor that I have to her. My dad on the other side, he was super, super fun loving. super open and creative. And he really fostered a huge sense of curiosity in myself. He always encouraged us to, or me specifically, to take apart things and experiment. You'll see this picture in the top right. This is called a potato cannon, which is a contraption you build out of the pipes you'd see in your plumbing in your house. And we would build cannons out of it that could launch potatoes hundreds of feet into the air. So I kind of view my mom really instilled this sense of rigor and working really hard. And my dad really fostered this sense of curiosity. So that kind of situated me well as a child to just build things all the time. We would build various medieval trebuchets, these potato cannons. I bought a hang glider when I was in high school, just a lot of curiosity and playing around with things. That launched me off into college. Going from high school to college, even though I really worked hard in school, I wouldn't say I was that incredibly motivated to go to college. I was kind of rebellious and felt like going to college was conforming. So I didn't apply to many schools. I applied to one school. I applied to two schools. One I didn't get into, the other I ended up going to Drexel University. But once I started there, my first year, that was when I really started falling in love with robotics. A couple projects that I did while there, building a drone, building a couple other small robots. That was the first time when I really delved into the full stack of building a robot. So designing the hardware, doing all the electronics and the wiring, and then like you guys were exposed to today, also doing some of the software and programming. And seeing all those three aspects of it come together and seeing the robot come to life, seeing it respond to some of the conditional statements I had programmed, that was kind of my big aha light bulb moment where I felt really empowered to just think of something in my head and then being able to create it and sort of breathe intelligence into it. So in college, I just spent a ton of time using every excuse I could find to do projects. I would turn my independent studies into research projects where I would design robots like these ones down here, and use every opportunity I could to compete in competitions and whatnot. So I did want to take a moment to talk a little bit about projects in general, side projects. I think that's a huge part of every engineer, whether you're in high school like you guys are or in college, figuring out what you want to do with your life. Projects are just a great way to really understand all the problems you would never even think about. You know, you're learning about math and physics, and that stuff is really hard and complicated, but you might not be thinking about communication protocols for a robot, or like, what does a ball bearing do? Or, you know, how do you go from code on a page to robot moving in the world? So side projects are a really, really good way to do that. And I also wanted to just show an example of a couple lines of code. So you guys did some block programming today, which is a little more graphical, dragging things and dropping them. These 3 lines of code here are an example of some Python code that's fundamentally the same thing that you guys are doing, programming loops, getting stuff to happen in those loops. And this is it being applied to this robot here, this side project, I call it Penny, in order to get it to drive around in the world like you're seeing here on the right. So we have a loop right here for I in range 4. This is just looping from 0 to 3. So there's 4 different numbers there. And then in each of those loops, we set a wheel angle, which is this little motor right here, aiming the direction of the wheel. And then we set a drive speed, which is setting the rotation speed of this wheel. So this is real code that actually runs the robot. And it's just showing, you know, even though you're doing the fundamentals today, it really does map to how robots work in the real world. From college, I got a really cool internship that launched me into my first job at the Naval Research Laboratory. I worked on the spacecraft's mechanisms group. That group is responsible for designing parts on satellites that move. So things like hinges and deployment mechanisms. You can imagine a solar array that unfolds. One of the main projects I worked on was this little tool in the top left that's meant to dock with satellites in geosynchronous orbits that are moving at the rotation rate of the Earth. So this tool would go up against a satellite, grab what's called the Marmon ring, this structural part at the bottom. And once we're docked, we can then do things like refuel it, push it into a different orbit, attach payloads. And that was a really, really cool project. At the Naval Research Lab, I really learned a lot of the hardcore fundamentals of engineering. I had done a bunch of side projects where I built robots that did cool things. But when it got into satellite engineering, that was just a whole new world of detail and rigor I had no idea even existed. Things like materials expand ever so slightly when they heat up and get cold, and accounting for that thermal expansion is super critical in for designing satellites. Outgassing, designing for fatigue instead of just brute strength. So a lot of really, really good fundamentals. I'm super thankful for learning there. While I was there, though, I also did some other non-space projects through a couple grants. This is a quadruped I designed that runs off of hydraulics. And this is a lot more kind of fast and loose cowboy style engineering. And one of the biggest differences when I reflect back is that, satellites, they have to work. You're investing hundreds of millions of dollars just in your ride to space, and then more hundreds of millions of dollars in designing the hardware and testing it. So everything has to be absolutely perfect, a ton of testing. That leads to a little bit slower pace, which is totally necessary for the level of risk and the severity of the repercussions if something messes up. Whereas on the terrestrial robot side, normal robots meant for here on Earth, those could be a lot faster. It's a lot more willing to take risks. And I really just fell in love with that faster pace of engineering, both in developing quicker as well as just there's more power and speed involved in these systems. So that kind of launched me to Boston Dynamics, which is the job I'm currently at. I've been here about 6 years, and it's been a really great time. I'd say the first half of those 6 years was just kind of like a kid in a candy store doing really, really fun projects. I was a part of a small team, maybe 5 or 6 of us on the Atlas team, designing upgrades to the robot you've seen all around YouTube, and upgrading some parts to be stronger or to have a little more power in the battery. A lot of fun there. I worked on Stretch for about 1.5 years, designing the smart gripper, we call it, which is meant to pick up boxes and individually actuate these suction cups. But then the last 2 or 3 years-ish, the company kind of pivoted Atlas in a direction more towards production. And that marked a pretty stark change in the type of work I did and the type of interactions. And that led to a bunch of hires, a much larger team size, a ton more factors to think about when you're designing a product that is going to be in the world versus a research and development prototype like the hydraulic version of Atlas there. So that was obviously a big change for me. And I'd say probably the biggest change was not so much in the technical work that I was doing. There's still a lot of really hard problems to solve. But it was more so in what it means to work as a team. We went from 5 or 6 people to 15 to 50 people over the course of a matter of months. So I really learned a lot about what it means to collaborate and what it means to listen. And so I just wanted to take a little bit of time to mention that teamwork in the way you interact with your coworkers, and for you guys, the way you interact with your classmates on projects and just in life in general is really, really important. Because when I arrived at Boston Dynamics originally, I was just like, I'm here for the robots. They're awesome, super cool technical stuff. That's still the case. I love the robots. But what is really the most compelling thing now is working on an awesome team and having great coworkers and really designing robots like a family. And there's just a couple more things I'll get into later, but shifting from that technical to kind of focus more on collaboration and how to work as a team has been the past couple of years here at BD. But let's move on a little bit. I want to talk a little deeper about technical stuff now. So I figured I'd start by telling you guys about the anatomy of a robot. So you went ahead and you programmed some sprites that move around on your screen. When it gets to the real robots in the real world, there's a couple key ingredients that they all have. One of them is a computer. So every robot that wants to move in the world autonomously needs a way to make intelligent decisions. That can be anything from deciding where you're going to place your next foot, or deciding the path you're going to fly if you're a drone, or picking a route on the ground if you're a vehicle. High-level decisions about taking in instructions. It can also be lower-level decisions like, am I going to have my elbows oriented like this or like this? And how am I going to support the weight of an object and not tip over? Another really important aspect is sensors. So, you develop sprites today that are trying to follow walls and take turns. A big part of our robots is being able to make decisions based off of the environment around them. So this is an example of a stereo camera that gets both visual data as well as depth data to see how far away things are. There are other sensors like force sensors that might sense when you're pushing on an object, how heavy it is or how soft an object is. There's sensors like an IMU, an inertial measurement unit, that measures the angle of a robot. So all those sensors are really important to let our robots move in the world intelligently when there's disturbances, when there's debris on the ground, not fall over, and be successful in their applications. Moving on to the hardware side of it, the actual thing that makes the robot move is batteries. That's a huge part of robots. This is an example of a battery that's sometimes used in robots, kind of like a big AA. And we take a ton of these in parallel. Just like your remote control might have 2 batteries, we put dozens and dozens of these batteries in our robot to give a battery pack that will meet our power requirements, last long enough, meet the voltage requirements that we need. And that's what lets our robot not be tethered to a wall and walk around where we want it to. And then lastly, a really big deal is the actuators, which is our word for a combination of the motor and the gearboxes that let our joints move on our robot. So here's an example of a rotary actuator. And you can see them. They're used in our elbows, shoulders, all over the place. The majority of these actuators on robots are rotary, as the name would imply. They spin just like your elbow bends. But some of them are also linear, so they will do push-pulling. For example, the ones here in the back are push-pull actuators that let the robot also tilt its back. So that's kind of the basic anatomy of a robot. If it's a wheeled robot, instead of these types of actuators, you might just have a motor that spins a wheel, or for a drone, it might be a motor that spins a propeller. But you can kind of still boil things down to those 4 components. And then a little bit, you guys learned all about software. I felt like it would be good to also talk a little bit about the control side of our robots, because that's super important. And while I'm on the hardware team, I can speak a little bit to the software that runs on our robots. One of the things that people get most excited when they see our robots is, like I mentioned, the fluidity and the fact that they almost seem biological in the way that they move. So you see the old Petman prototype here. When it gets hit by a weight, it kind of regains its balance, similar to as a human might. And a lot of that comes down to really good sensors and really good programming and controls algorithms. So here's a couple examples of some sensors that you might have on a robot. This one right here is a force torque sensor, and those are often put in the ankles, and that lets you sense where the weight is on your foot. If you were to stand on a foot and close your eyes, you'd feel your foot moving all around and putting your weight on your toe and then on your heel and on the sides of your foot. Similarly, we want our robots to be able to do that in order to maintain balance. So we use sensors like this to position the weight and maintain balance. Another really common sensor I mentioned before is the inertial measurement unit. You have those in your phone. The overwhelming majority of robots have these inertial measurement units, and that can be used to measure the angle that you're tilting at. It can be used to measure how fast you're rotating. And so in this case, the robot is sensing disturbances with an IMU, and then it goes to regain its balance by swinging its arms like that. And then lastly, I also just want to give one more example showing how a couple lines of code, a for loop, just like you guys are programming today, can be used to also breathe intelligence and controls into a robot. So here's that robot. I mentioned Penny, and I'm testing out a control algorithm on it. I have strapped to my vest an IMU that senses the angle of my body. And then also in the foot pads here, there's some weight sensors that sense whether my weight is on the left foot or the right foot, or my toe versus my heel. And this is an example of some real code that, in this case, I think I was using the weight sensors on the foot. I would sense where the weight is, say 100% weight on the left foot, and I would command an acceleration of the robot. So just like you learned in physics class, acceleration means you're speeding up or slowing down. So I would, based off of the weight shift of the pads, I would speed up or slow down. In this case, I'm slowing down. And then I convert that into a velocity of the wheels. And you may have remembered in that one up here, we command a wheel sensor, set drive speed. So that's an example, again, of using sensor input to command a robot motion that works in the way that you intend. All right, so we're going to move into the last part of the presentation, which is talking a little bit about the day-to-day of an engineer, the types of things that we do, and a couple lessons learned from that. So I'll first speak about design and 3D modeling, which is a big part of what mechanical engineers do. When you see one of these robots on screen, doing these things, that all started as some idea in someone's head. And a big part of going from idea in your head to physical robot in the world is being able to get those ideas on paper or on a computer screen. So 3D modeling is a big aspect of that. So we use software. This is, an example of what some of the software looks internally, to draw various shapes and get an idea down onto a screen. So you can kind of think of this like a sketchbook of sorts. And we still use sketchbooks, but we'll quickly transition from drawing things on paper to drawing things on a screen in 3D, because the packaging is so dense and we really have to be precise in our measurements. So that's a big part of mechanical engineering, is the design. Another really big part of it is how these designs develop from when it first enters your head until it goes out to be fabricated and made. And these designs are super complex, as you might imagine. And one thing I really wanted to emphasize was, how do these designs evolve from an idea all the way through? And a big part of that is taking feedback as an engineer. I've been really fortunate to be a part of a lot of concept designs. Some positions you might inherit a design that's already 80% mature. In a lot of cases, I was fortunate enough to kind of be in roles where I had to think of the initial idea and then carry it all the way through to fabrication. And one of the biggest lessons I've learned is that getting feedback from other team members is absolutely essential. One of the biggest strengths of Boston Dynamics, I would actually consider to be psychological safety. And what I mean by that is, when someone has an idea that's potentially seemingly stupid or a bad idea, still feeling enabled and comfortable speaking that up or bringing that up, and not being judged when they bring up a bad idea. And I have done that so many times. I've had so many just terrible ideas. But thankfully, we've been in an environment and a culture where when you bring up ideas that are bad, people don't shoot them down and throw them out. You do have to make progress, so you're not just going to listen to everything, but really the way you treat people kindly and generously in these design reviews is super important. So as you're, working in projects with team members and figuring out how to work as a team, I would just really encourage you to take feedback that you receive graciously, and then give criticism kindly in how you're interacting with people. And I can't tell you how many times the design I've owned has just totally morphed from something, the thing that I imagined, into something that's so much better, because the input from coworkers is just really, really helpful. All right, moving on to the second aspect of mechanical engineering that I want to go over is math and analysis. I'm sure your teachers have told you plenty of times, learn this stuff because you're going to use it someday. I'm here to tell you that you do actually use it someday. And it can be really exciting and fun seeing all that stuff you learned in school being applied in real life. So this is just some examples of types of things that we might look at. I'm not going to go into what this actually means, but we do a lot of plots, a lot of coding, not just code that lives on the robot, but code that's used to optimize designs or figure out if a design is going to work or not. So I think the one thing I wanted to say about using math in class versus on the job, this is a little bit of a personal take, but I felt like in high school and in college, you really went through the rigor of like learning how to take a derivative, or learning more fundamentally what sine and cosine means, or like solving a bunch of algebraic equations. On the job, there's not as much of actual solving these equations. We have tools and calculators, fancy calculators that do that all for us now. But gaining that intuition, really understanding concepts like derivatives and integrals is really the important thing. And the only way to get there, in my experience, is to go through the laborious process of deriving equations and doing all the algebra and growing that intuitive understanding. And then once you're on the job, you have all these things to help solve these equations for you, but you still really need to understand intuitively what's going on. So like algebra, for example, I'm not solving algebraic equations that frequently, but I'm constantly thinking about the relationship between maybe torque and speed, or are two things inversely related? Is there a quadratic relationship between two terms? And that algebraic foundation was just absolutely essential in being able to think certain ways as designs evolve. Trigonometry, likewise. You guys probably know way more about trigonometry, or you will by the end of high school, than I have remembered now in terms of deriving equations, but understanding really like what sines and cosines mean, and being able to, again, think through relationships using these functions is really important. Calculus as well. I don't remember how to derive most calculus functions, but derivatives and integrals are frequently recurring topics that come up. So do well in school. That's really important. It does get applied in real life, but I'll leave it there. All right. So there are a ton of other really fun design factors. I just mentioned two aspects. A couple more, and there again, there's plenty more, are manufacturability. How do your parts get made? Working in machine shops will teach you a ton about how to actually go from like a theoretical idea of a shape in your head to actually making it. Thermal management. Our human bodies are incredible. Biology is incredible at managing heat, dissipating it through things like sweat. Crash loads. This is one that's pretty fun and unique to legged robots. We do all these crazy backflips and fall over. And designing structures that can withstand those impacts is really hard. Even knowing what level the impacts of force are going to be at is really hard. And then one more I'll mention is sealing. We want our robots to work in all sorts of environments. If they're being rained on, we want our robots to still be able to operate properly. So those are just a couple snapshots about the other things that we think about, and there's a ton more I'm not going to go into. But as you spend more time engineering, you just learn more about these topics, and you go ahead and you apply them to your designs. All right, this is the last slide I had, and it's about testing. So you design your robot, you build it, which I'm not going to get into manufacturing here, but the next big thing is to go out, test your robot in the wild. So I'm going to show a brief video here showing a couple of the highs and lows of what testing really looks like. right. So hopefully that gives you a little snapshot of what it's like to develop robots in the wild. There's a lot of failures, a lot of successes. I remember one of our biggest recent successes was just a couple weeks ago. It was the first time our robot did backflip. You had about 100 of us gathered around, and the first attempts went to do the flip, and it totally just nailed it. And that's the first time in my career here that we've done something that level of complexity, first time on hardware, and it just worked. It was amazing. So there's a lot of really high moments like that, and there's also a ton of really hard moments of failure. And I find that actually a lot more interesting is thinking about failure and how to deal with that. I've had a lot of personal failures. The teams have had a lot of failures, and what you do with the failure, I think, is a lot more important than the failure itself. Good. They keep you humble. And if you learn from a failure, then I would consider that's actually a pretty big success. And really responding to it, leading you more towards curiosity than fear is really essential. So I'm sure you guys all have a lot of good successes and failures ahead of you. And that's just my take on that. A couple other things, again, just some random rapid fire lessons learned over my career is time management is super, super critical. I found that when I was able to kind of get things like Netflix, doom scrolling, gaming under control, my rate of learning just absolutely skyrocketed. So yeah, managing your time, being able to put a lot of work in is really, really helpful. This is a pretty common one, but following your passions is critical. I was really fortunate to have a career where my personal passions really aligned well with the type of work that we do. Not everyone is that fortunate, but I just encourage you to really explore that for yourself and figure out what you want to love to do. And then last but not least, I think the biggest thing is just learning how to be kind to others, how to treat people well, and stay curious in everything you do. So that's going to be a lifelong lesson for all of us, but I would just encourage you to think about that as you guys go forward. And that's everything that I had. Thanks.
Yeah, thank you so much. That was a wonderful look at everything involved in what you do on a daily basis. And I'm wildly intrigued and want to visit you just to walk around with you for a day and see what kind of crashes I observe. But hey, students, teachers out there, are there any questions? Things that popped up. There were a lot of things that we were exposed to there in terms of robots, how they're built, and different considerations, different disciplines. Does anybody have any questions out there? See if we can.
I do see one question in the chat, Pat, and if you want me to read that out, just let me know.
Yeah, please do. Thank you.
Sure. So this is from Eric Einset. He says, really interesting, Josh. Thank you. You showed some code written for controlling the physics of how the robots move. Do you also use AI and deep learning models in your robotics? And if so, is BD training their own AI models?
Yeah, I can give a decent answer to that. I'm on the hardware side, so I'm not going to, maybe have as much confidence as someone here on the software side, but absolutely there is a ton of AI going on. The AI means a lot of things to a lot of different people. The fundamental thing for me that it means is that element of training, like you alluded to, like you mentioned. So yeah, there's a ton of training going on for all different things, all the way from top level robot control down to lower level things. We do use a combination of both classical traditional controls as well as models and reinforcement learning and whatnot. So that's pretty typical now. I think you'd be hard pressed to find at least humanoid robotics companies that don't do a lot of AI.
I do see a couple questions. Jillian, you want me to tackle these?
Yeah, go for it.
Yeah. So there's a young lady named Sophia, and she's wondering what the hardest thing about your major was. I believe it was mechanical engineering. Was there a minor involved or something specific, or just generally mechanical engineering?
I was just, a mechanical engineer. I did a lot of robotics related things in college. I'd say the hardest thing was, I don't know how to put this, but kind of taking my education by the horns to make it something that was valuable for me. I think every school has its pros and cons, and for me, that was like having a good relationship with the machine shop, so they could teach me how to use mills and lathes, and talking to professors to get into labs so I could get access to higher end hardware. And a lot of sort of taking initiative and being assertive to get a good experience in college, rather than more of a vanilla one, really helped me just move at a faster rate and learn some maybe more advanced things from school.
Very good. Awesome. This is more specific personal question. Somebody's wondering if you know Benjamin Stevenson. It's their ELA teacher's cousin.
Oh yeah, Ben is a super central role on the Atlas team. He's on the software side of things, but yeah, we collaborate fairly frequently.
That's so neat. Tell him hi from Oklahoma.
Will do.
Thank you.
All right, sorry. And so sorry, I was waving somebody down here. There's Alan, and he's going to major in ME and wanted to know what the most interesting class that you were during that process that you took, possibly. There's a lot of variety of classes, fluid dynamics, maybe a little structures.
Yeah.
There's a lot to choose from, I bet.
Yeah, this one it was a little earlier on, but I'd say probably just my statics and dynamics classes. Or actually, I'd say mechanics of materials. So I think the first time that it really set into like stress strain curves and how to do free body diagrams and analysis, that was a big clicking moment in mechanical engineering.
There's a question here that talks about what is the main purpose of your robot, and that was one of my questions. You're doing some really cool stuff with a variety of robots. Atlas, in particular, doing some jumping and climbing. Some movements are smooth and the balance works sometimes and doesn't work other times. What is the main goal, do you think, of your process, and what the robot, like all the learning that's going on in terms of making it better and smoother and more human-like? Is there an end goal for what you'd like for your robots to do?
Yeah, our robots are targeted primarily at.
Were you able to get Kate's balloons? Okay.
Our robots were targeted primarily at industrial automation, and so you'll probably see a heavy focus on moving car parts or manipulation that is really hard for traditional robots like a giant KUKA robot arm to do. So you'll see it mostly in warehouses where it can be safe and there's controlled environments. Definitely there's desire to do more in the world and with a grand goal of just universally helping people, but the entry point is definitely going to be more so focused on industry.
Okay, and I guess a quick follow-up. I know there's one of the things that we discussed, and I may not have mentioned in the intro, is the purpose of robot, like in terms of folding laundry, or maybe in more serious environments, rescue, and maybe in dangerous environments to be able to kind of come into an environment that might be dangerous in terms of explosives and things of that nature. Are you thinking about those things in the background in terms of the functionality of your robot? Is that kind of one of the objectives, or does it depend on the project?
Oh yeah, I mean, you may have heard the saying "dull, dirty, and dangerous," and we definitely abide by that. I think Spot is a great example of that. It's been deployed to sites with radiation. It's been deployed on search and rescue. There's been a lot of cases where those are jobs where the last thing you want is a person to be there. So Atlas is a little more targeted towards industry because it's newer. But Spot, there's a lot of really cool applications that it has gotten into.
Cool. Quick question about what's behind you. It looks like a hockey mask kind of situation there, and the wall behind you. Somebody was wondering what those are.
Oh yeah, so we moved into this building maybe 4 years ago, and what they did was they went through this old warehouse where we stored all of our old robot parts at from old generations, and they just picked through all of it, and they made a bunch of this wall art here from all of that. So I believe that's the torso shell of one of our humanoid robots that was turned into some wall art.
Yeah, that's kind of cool looking. Yeah. want to make sure I'm not missing any questions. I think there was one, this is kind of a big picture one, it seems like. How do you think engineering will change in the next couple of years, maybe 5 to 10? And that was their question. So what do you think? Like, you've seen things evolve over the 6 years you've been with Boston. I'm wondering, what do you see the job and what you're doing in your job changing in the next 5 to 10?
That's a really good question. I'm going to answer that from the perspective of a hardware engineer as opposed to a software engineer, because that's what I do. I can't imagine, that seems a lot harder to answer as a software engineer. There's a lot of parts of my job. I mean, it's really hard to predict something 5, 10 years out. That's a long time, the pace things are moving. But there's a lot of things in my job that I think are fundamentally really hard to automate or replace with any sort of like AI model that I see coming around. And we get people reaching out not too infrequently asking us to trial, 3D modeling programs that are AI powered. I think there'll be some low level workflow speed ups, but by and large, the decision making and a lot of the brainstorming, I don't really see as changing too fundamentally. That's just those are just types of things that are really hard to program or make some feedback loop to train around. So short answer, I don't see it changing too drastically in the next 5 to 10 years.
Sure, fair enough. There was a question about industries you'd like to join, and actually that prompted a question in my brain. You working with satellites for a little while, and then saw an opportunity with Boston Dynamics. Seems like two, kind of not wildly separate, but a little bit different industries in terms of using your skill sets. Did you find that transition a little challenging, or were there a lot of skills that rolled over from one to the next?
It was a pretty, all things considered, I think it was a good transition. It's kind of interesting. We get a lot of roboticist type candidates, and then we also get a lot of just general mechanical people. And then I found that if I had to pick between someone who knows a lot about the concepts of robotics versus someone, say, from like automotive, who does really, really good machine design and understands the nuance of fits and tolerances and various other mechanical things, a great mechanical engineer is a lot more valuable than someone who has a really good background in robotics. So in that sense, like thermal expansion is a huge factor in designing robots as well as satellites. And a lot of the core concepts do translate. I think on top of that, I was doing so many side projects that were robotics related while working on satellites that the transition was pretty seamless. And I always kind of, maybe this is growing up with lots of siblings with a lot of chaos, but I just loved fast moving things, power, speed. I was kind of like always a power junkie in the types of robotics designs that I would do. So I kind of always felt like Boston Dynamics, it's literally in the name, Dynamics, was always a really fitting place for me.
Sure, sounds like it is. Eric has a question that I'm fully on board with asking, because it came up when you were talking about all the situations where you fail, quote unquote, and they fall down, didn't do what you wanted it to do. His question is, how do you start figuring out what went wrong? And my kind of related question would be, at some point, are you testing the failure and saying, how far can we go with this? Or is that too expensive of a process to go through? And as far as the materials themselves, are you testing them maybe individually, like this particular structural piece, elbow, waist, things like that? Are you doing that separately and in-house? Or is that something you put it together and then kind of see what happens? Those are a lot of questions in there, but hopefully you get the gist.
Yeah, I think generally the answer is yes to everything. We test at all sorts of different levels. We test things to it's like target life, where we're giving it the loads that we expect it to see. We also do other types of testing like halt testing, highly accelerated life testing, where it's meant to, it should fail. And that more so isolates the weakest link, even though you might never see those loads in operation. So we do both of those types of testing. In terms of debugging and figuring out where failures are, a huge thing is our logging capabilities. So every time the robot runs, we're logging thousands of variables, thousands of times a second. So a 2-minute run of a robot walking around, we're generating, we can generate gigabytes of data from that. And we can sift through all that before we ever take the robot apart and look at any parameter we really want, as long as there's a sensor on it. So the sensors are good for working in the world, but they're also really good for diagnosis. And then that kind of launches us into isolating, all right, we think it's the elbow joint and maybe there was a short circuit or something there.
Excellent. That really, this has been a wonderful conversation. So I think we're going to end with that. And thank you so much for your time. It was a wonderful, really great presentation. And it gave, I know myself, I learned a lot about what you do in a given day. And it sounds really exciting. And it sounds like a really wonderful, supportive group. And so I do hope our students out there get a chance to involve themselves with the company like that. So thank you so much for your time, Josh.
Yeah, thanks so much, guys.
Absolutely. A huge thank you to you, Josh, for sharing, man, your upbringing, your story, your successes, and just as importantly, your failures. And I think Mr. Lee said, thank you for sharing your perspective on failure and how it can end up being a win, right? Thank you to Pat Marshall. You absolutely killed it today as our engineer lead. Thank you so, so much. Thank you to ET staff who's behind the scenes making sure everything is running smoothly. And most of all to the teachers and students, thank you guys for joining us and hanging out with us today. Hope you had fun, hope you learned, and hope to see you at our next event, which is January 30th for pharmaceuticals, and we'll drop the flyer, okay? Look out for an email with today's full recording, and enjoy the rest of your day and take care. Thanks so much.
Thank you so much, everybody.